Planet Semicon welcomes you to explore the field of semiconductor physics and technology, the foundation of microelectronics and VLSI design engineering.
Welcome to this video on timing analysis in VLSI design and factor influencing the ASIC timing characteristics. Timing behavior of a ASIC design is strongly influenced by the material and structural parasitic. RLC parasitic of wires and vias introduce unwanted circuit delays. Logic gates parasitic further add the intrinsic and load-dependent delays. These factors impact the timing delays of paths that are made up of combinational and sequential logic elements. In sequential circuits, setup time and hold time creates a timing window and clock-to-Q delay define the speed of data transfer. Timing window constraint violation leads to logic errors or metastability. Static timing analysis is used to verify design timing paths violations and ensure faithful data transfer across the timing paths. In this video we will review the above issues and, in the upcoming video, proceed to static timing analysis. So, let's get started. Every functional element in VLSI, whether a MOSFET, interconnect, or contact, is made of real physical materials that possess finite resistivity and dielectric properties. These materials do not behave ideally, instead, they introduce parasitic resistance, capacitance and inductance as an inherent part of their structure. Because electric and magnetic fields do not stop sharply at geometric boundaries but extend into nearby regions, giving rise to fringe and coupling effects. At nanometer scales, these field interactions become dominant, affecting how charge and current flow in the circuit. The result is that every transistor or interconnect behaves as a distributed RLC network, rather than an ideal lumped element. High electric fields in short-channel devices introduce second-order effects such as velocity saturation and DIBL, further altering timing and current behavior. Interconnects are the physical wiring structures that carry electrical signals and power between various functional elements. Structurally, an interconnect consists of metal layers, vias, and dielectric materials. The interconnects are not just physical wires but functional elements that define circuit timing, power, and noise behavior. These layers, due to their electrical fields, create parasitic capacitance between the interconnects. The geometrical parasitic created are of three types, namely, area, overlap, and sidewall capacitances. The area capacitance is created due to overlapping surface area between the metals and to the substrate ground. The overlap region occurs due to vertical alignment of interconnect. The sidewalls of interconnects, where the metal's vertical edges face neighboring lines, generate sidewall and, due to electric field spreading, creates fringe capacitances. To optimize die area, the interconnects are routed vertically in different layers. The parasitic are minimized by routing successive layers in horizontal and vertical directions. Self-inductance is a single conductor phenomenon wherein a source current flowing through a conductor creates a magnetic field that induces an opposite current in itself, which opposes the very source current that created it. Mutual inductance is a two-conductor phenomenon, wherein the current flowing in one conductor creates the magnetic field that links with the neighboring conductor and generates an induced voltage. The loop inductance is a phenomenon created due to the flow of source current and the ground plane return current. The source current and the ground plane return current produces opposite magnetic field and, together form a closed magnetic loop. The increased enclosed current flowing path area increases the loop inductance. These inductive parasitic distort waveforms and degrade timing accuracy. The clock net paths experiences jitter, skew, or edge ringing, and impacts the timing performance. Every MOSFET, apart from its ideal behavior, as shown in the figure, inherit parasitic resistances, capacitances, and leakage paths. These parasitic arise due to physical layout, material properties, and junction structures in silicon. The gate-to-source and gate-to-drain capacitances contribute to the input loading and delay. The Miller capacitance between gate and drain amplifies the dynamic power and slows switching. Source and drain series resistances limit current flow, reducing transconductance and drive strength. Substrate coupling introduces noise and crosstalk between nearby devices on the same chip. Junction capacitances between diffusion regions and the substrate increase with area and doping. Leakage currents through body diode and gate oxide degrade the static power efficiency.
MOSFET is a voltage-operated device, with forward transconductance gain and is associated with several inter-electrode parasitic capacitances. The driven CMOS gate being a capacitive load, along with parasitic gets charged and discharged, creating current transitions. The CMOS gate delays in addition to input transition time and load capacitance depends on several complex, nonlinear effects and phenomenon. In modern CMOS technology devices, traditional linear models fail to capture complex and nonlinear behavior of short-channel effects, velocity saturation, tunneling, etc. Nonlinear characterization evaluated under various operating conditions provides more precise representation of complex behaviors that helps verifying and modeling. Typical CMOS inverter timing parameters measurement method is described below. Time between 10 to 90% of rise or fall transition is defined as rise or fall time. Propagation time TPD is defined as the time elapsed between 50% of input and output signals. The time elapsed between 50% level of input low to output high is known as TPD-LH. Time elapsed between 50% level of high input to low output is known as TPD-HL. Propagation delay TP is defined as the average of sum of low to high and high to low propagation delays. Contamination delay TPD is the propagation delay of the logic gate without external load.
The figure shown illustrates the timing behavior of a latch and a flip-flop. The clock or enable signal enables the data capture of the storage devices. In the case of a latch, data at the input D is transparent and passes to the output Q as long as the enable signal remains active, making the latch a level-sensitive device. When the enable signal goes low, the latch stops tracking the input and holds the last valid data value at its output. The flip-flop, on the other hand, captures data only at a specific clock edge, either rising or falling, making it edge-triggered. At that moment, the input D is sampled and transferred to the output Q, which updates only once per clock cycle. This creates a distinct difference in timing behavior. Latches remains in transparent mode during part of the enable period, while flip-flops impose strict timing boundaries between clock edges. As a result, flip-flops are commonly used in synchronous designs, whereas latches are useful. The time optimization is needed. Together, they form the fundamental storage and timing elements in sequential digital circuits.
A data or a delay latch is a fundamental building block in sequential circuits that store and hold data based on the control signal, often referred to as the clock or enable signal. They come in two types based on the level of the clock or enable signal that activates them. A positive level D latch is active when the enable signal is high, that is at logic 1. A negative level D latch is active when the enable is low, that is at logic 0. There are different configurations by which a latch can be implemented and differ in characteristic parameters. A simple configuration of implementing a positive and a negative latch is shown in the figure. A latch consists of a data transmission path and a feedback loop. The data path, consisting of transmission gate and the inverter, transmits the data. When the path is enabled, latch operates in transparent mode and propagates the data into the latch. As long as the latch is disabled, it operates in hold mode and the feedback loop retains the propagated data stable. A simple schematic of positive edge D flip-flop is shown in the figure. A positive edge triggered D flip-flop is made up of two latches connected in a sequence. First, a negative level sensitive latch is connected in series with a positive level sensitive latch. This combination of latches creates a positive edge triggered flip-flop. This configuration ensures that the flip-flop captures input data D on the rising clock edge signal only. The first latch is known as master and propagates the input data D at the clock transition. The second latch, known as slave, propagates the captured data into the output terminal Q. The first latch, known as master, within clock at logical low, operates in transparent mode and captures input data D. The second latch, known as slave, with clock at active high, operates in hold mode and retains its previous data at the output Q. Subsequently, at the next positive clock transition, the latch will operate in transparent mode and will be as ready to capture the next input data. Timing characteristics of a flip-flop. Due to the transmission gate and inverter's timing delays of the master and slave latches, the input data must be made available in advance for a specific period of time before and after the clock edge transition occurrence. This ensures faithful transfer of the input data D to the output Q. The period for which the data should appear and be stable at the input terminal before the clock edge is known as setup time and after clock edge is known as hold time. Sum of the setup and hold time period combinedly is known as the timing window of the D flip-flop. This ensures correct capture and transfer of the input data by the flip-flop. The propagation delay of a flip-flop is defined as the time period that elapses between 50% level of input voltage appearing at input D to 50% level of output voltage appearing at output Q.
In a master-slave latch, the negative master latch is transparent when the clock is low. Its propagation delay is expressed as sum of the delays of transmission and the forward inverter gate. The positive slave latch is transparent when the clock is high. Its propagation delay is the sum of the delays of transmission and forward inverter gate delays. Setup time is the time period before occurrence of the clock edge. The input data has to arrive and get stabilized. The setup time is made up of sum of the delays of the master transmission gate, forward inverter, and a safety margin. Hold time defines the period after the clock edge, during which the received data has to be retained and remain stable at the input. The hold time is expressed as sum of the delays of the slave's transmission gate plus feedback inverter delay minus the master's delay. Clock to Q delay reflects how quickly the output responds after the clock transition. The overall clock to Q delay is dominated by sum of the delays of slave latch plus wire and load. The sum of setup and hold timings is known as the timing window. It with respect to the clock transition defines the period for which the input data has to arrive and remain stable. These timing constraints ensure correct data capture and prevent metastability. The diagram shows the relationship between input, D, clock, CLK, and output, Q, signals of a D-type flip-flop. A D flip-flop captures the input data precisely at the active clock edge, typically on the rising edge. With the clock transitions from low to high, the flip-flop samples the D input and transfers it to the output Q. Between two clock edges, the output Q remains constant, holding the previously latched value. The setup time is the minimum period before the active clock edge during which the D input must remain stable. The hold time is the minimum duration after the clock edge during which the D input must continue to remain unchanged. The region defined by the setup and hold intervals is called the timing window or aperture time. For correct operation, input data transitions must occur outside the timing window, ensuring stable capture. When setup and hold conditions are satisfied, the flip-flop output Q transitions cleanly in response to the clock edge. The output waveform in the diagram shows that Q follows D, but only after each valid clock edge. If data changes within the setup or hold interval, the flip-flop may enter a metastable state, causing timing uncertainty or incorrect output. In synchronous digital design, flip-flops rely on precise timing between data and clock signals. The timing window defines the safe interval around the clock edge, where data must remain stable. This window spans from T setup before the clock edge to T hold after it. A setup violation occurs when, with respect to the clock edge, if the data arrives too late, that is, if data changes in the setup timing window, the flip-flop may not capture the data reliably. A hold violation happens when data changes too soon after the clock edge. The data change in the timing window results in a metastable state wherein the output Q hovers unpredictably between 0 and 1. Then the flop enters into an oscillatory state wherein the output has no relevance to the input data. The resulting flip-flop output waveforms under metastability condition is shown in the figure. ASICs are fabricated using stack of patterned different material layers. Its performance depends on the fabrication processes employed, voltage, thermal and environmental operating conditions, packaging, second-order effects, fringe fields and so on. Impact of some of the influencing factors are discussed below. Fringe fields occurring due to electric field lines, extended beyond the conductor edges, create stray capacitance and cause parasitic capacitive loading, and signal delay. During fabrication, the proximity and pattern-dependent effects stem from edge bias and line edge roughness, which alter the wire geometry and impact resistance and RC delay. Switching transients create interconnect heating and rise the net temperature, leading to increased resistance and RC delay. Voltage or IR drop, resulting from resistive power grid losses, reduces the gate drive strength and impacts critical timing paths. Electromigration is a process in which atomic physical displacement takes place along the direction of current flow, leading to creation of voids, the reduced net cross-section, and helix, the increased cross-section. Over a period of time, this leads to increased RC delay and risk of catastrophic failure. All such second-order phenomenon put together impact the timing closure and signal integrity, performance and product reliability. In VLSI design, functional correctness alone is insufficient. The circuit must also operate within the required timing constraints. Timing analysis ensures that signals propagate across the physical layout of the chip, without violating the timing window. When a gate-level netlist is placed and routed on silicon, different timing paths emerge. At gate-level netlist, timing is estimated using Characterized cell models. After placement and routing, parasitic of interconnects are extracted. Timing analysis with back annotated of parasitic ensures the physical layout still meets the design's timing constraints. Timing analysis in VLSI design is essential to bridge the gap between the logical netlist representation and the physical chip layout, ensuring that every timing path from input ports, through logic, to output ports meets design specifications. In VLSI design, timing paths are the networks that are made up of the logic gates and interconnects that are enabled by the control signals. Each timing path is constrained by several parameters and are to be analyzed to ensure the faithful data transfer. The paths as shown in the figure can be broadly classified as described below. The input to reg timing path starts from an input pad, passes through the combi logic and ends at input pin of the flip-flop. The reg to reg timing path starts from flip-flop input pin, passes through the combi logic and ends at next flip-flop input. This is the most timing critical path, and determines the maximum usable clock frequency. The reg to output port path starts from flip-flop input pin, passes through the combi logic and ends up at the output port. The combinational timing path starts from the input port, passes through combinational logic and ends up at the output port. The path elements of pin, ports, interconnect and gate are constrained by design and parasitic parameters that limit the operating frequency and may lead to metastability oscillatory condition. Static timing analysis is employed to analyze all the path timings and thereby ensure correct operation. Static timing analysis, or STA, is the backbone of timing closure in VLSI design. It computes delays across all paths, without needing input vectors. STA is fast, exhaustive, and pinpoints worst-case setup and hold violations. But it doesn't verify logical correctness or functional behavior. Dynamic timing analysis, or DTA, simulates real input vectors through the circuit. It captures actual data-dependent delays and detects glitches and hazards. DTA offers deeper insight into timing behavior but at a high computational cost. Large designs make exhaustive simulation impractical and expensive. In essence, STA ensures coverage and speed, while DTA reveals functional timing risks. Together, they complement each other: STA for closure, DTA for validation. Choosing the right mix depends on design complexity and verification goals. Timing analysis isn't just about speed, it's about confidence in silicon success. Thanks for your time. Timing analysis in VLSI design is not just a verification step, it builds performance and reliability into the design. From the parasitic effects in materials and interconnects, every component plays an important role in determining the overall timing accuracy. Understanding setup and hold times, clock-to-queue delays, and the significance of timing paths helps us appreciate the precision required in modern chip design. Hope this video has provided an overview of significance of timing path analysis of an ASIC design. Thanking you once again. Hope to meet you in the upcoming video. Bye for now.